Hi students, now we are going to discuss about some specially stabilized carbocations like cyclopropenyl carbocation, tropolium carbocation, cyclopropylmethyl carbocation, that is CPM carbocation, and aromatic aryl carbocations. Then polycyclic carbocations like cyclopropyl carbocation, cyclobutyl carbocation, cyclopenyl carbocation, cyclohexyl carbocation, how they are going to stabilize. Okay, I am explaining clear explanations to retain the concept in our mind and to choose the correct answer in the objective examination without confusion. Let's start now. First one is cyclopropenyl carbocation. Cyclopropenyl carbocation. The structural form I have to represent like this. This is cyclopropane. E double bond is there. Double bond. Cation, carbocation means positive charge is there. Okay. This carbon carrying positive charge is unstable. The stability you have to explain by applying the delocalization of pi bond electrons. First of all, you have to check it is aromatic or not aromatic. So you have to apply Huckel's rule, that is 4n plus 2 pi electrons rule. Here how many pi bonds are there? 1 pi bond is there. If 1 pi bond is present, how many pi electrons? That is 2 pi electrons are there. If 2 pi electrons are present means n value is 0, then you will get 2 pi electrons. N value 0 means then there is n value is not number of rings. It is integer value. It may be 0, 1, 2, 3, Okay. So that's why it is obeying Huckel's rule. So that's why it is a aromatic compound. It is aromatic compound, right? Now what happened? Delocalization of pi bond electrons was take place here. Yeah. So now what happened? These 2 pi electrons are delocalized from here to here. Okay. Yeah. That means these 2 pi electrons from here to here they migrated here. Then this carbon gets positive charge. These 2 electrons are back to these 2 carbons, right? When they migrate from here to here, then this carbon gets positive charge. Yeah. Then we'll get one resonance structure. Yeah, so here double bond and this carbon gets positive charge. Now this carbon carrying positive charge is unstable. Yeah. Now these 2 pi electrons, to stabilize that, these 2 pi electrons are migrated from delocalized from here to here. Okay, they migrate from here to here. Yeah. Then these 2 electrons migrate from here. Here this carbon gets positive charge. Yeah. Then we'll get these 2 pi electrons. Okay, then we'll get a resonance structure. So here double bond, and if double bond is there here, then this carbon gets positive charge. Yes. Then this is this carbon positive charge carbocation unstable. Then these 2 electrons migrate from here to here. Then we get structure 1. That means here you are getting totally 3 structures. 1, 2, and 3. You are getting now 3 resonance structures, right? 3 resonance structures. RS means what? Resonance structures. Okay, yeah. Now here the plus 1. How much positive charge is there on the carbon? Plus 1. The plus 1 charge, positive charge, is distributed. It is distributed between 3 carbons, that is in 3 resonance structures. Okay. So that the charge on each carbon, the charge on each carbon, how much you get? Plus 1 by 3. Yeah. That means the charge becomes from plus 1 to plus 1 by 3. It is reduced. Then the compound, that is the carbocation, is going to be stabilized readily. Yeah. Got it? Next one. Second one is Tropolium carbocation or tropolium ion. Okay, yeah. What is the structural formula of this? You can represent like this. Tropolium carbocation. So it is double bond, single bond, positive charge, double bond, single bond, double bond, single bond, double bond, positive charge. Okay, yeah. Here, this is a double bond, pi bond. Okay, here pi bond and sigma bond, positive charge. Wherever pi bond, sigma bond, positive charge is there, then that is called what? Conjugation. Wherever conjugation is there, the entire organic chemistry, wherever conjugation is there resonance is take place. Okay, yeah. Now these pi electrons are delocalized that can stabilize this carbocation. Here how many carbons are there? 1, 2, 3, 4, 5, 6, 7. Here there are 3 carbons. You get the 3 resonance structures. Here 7 carbons are there. You get 7 resonance structures. 7 resonance structures. Okay, yeah. That means here the plus 1 positive charge is distributed between these 3 carbons. There is 3 resonance structures. But here the plus 1 charge, positive charge is distributed. It is distributed between 7 resonance structures. Yeah. Okay. So that each carbon gets positive charge plus 1 by 7. So that the charge on each carbon, on each carbon is how much? Plus 1 by 7. Charge on each carbon is how much? Plus 1 by 7. Yeah. Okay. That means the charge is from plus 1 to becomes to plus 1 by 7. It is reduced. Then that is stabilizes this carbocation, tropolium carbocation, right? You will get the resonance structure of this. Okay, the resonance structure of this you can represent like this. Yeah, it is positive charge. Okay, so then the resonance hybrid you will get like this. Okay, here for this the resonance hybrid you have to represent like this. The positive charge is there, and here it is plus 1 by 3. This carbon also gets plus 1 by 3. This carbon also gets plus 1 by 3. Okay, this is a resonance hybrid. Got it? Here also this is a resonance hybrid. Okay, resonance hybrid RH. Okay, so here the positive charge is delocalized along, that is along the, so there is 7 resonance structures along the length of the carbon chain. So each carbon gets, it is plus 1 by 7. This is also plus 1 by 7. This is also plus 1 by 7. And this is also plus 1 by 7. And all this, each carbon gets plus 1 by 7. So that the charge is from plus 1 to plus 1 by 7 is reduced, so that it is easily going to be stabilized, right? Yeah. So this is the stability of tropolium carbocation. Got it? Is it clear? So this is the complete explanation. You didn't get the books properly in our available books. Okay, we are referring some foreign books, some different authors, that is in PG books. Okay, MSc books and research scholar books. So that's why you are getting the complete concept I am giving to you. Fine. Next, we move to next another one. Oh, can I erase it now? Yeah. There is foreign authors books we are referring. By referring different books, the complete concept, and to easy understand, I gave all these structures and resonance hybrid, how the charge is distributed on each carbon, right? Then it is crystal clear concept, so that's why I use the word. Next one now. The third one is cyclopropylmethyl carbocation. This is cyclopropylmethyl CPM carbocation. CPM means not this is a vertical part is CPM party. This is cyclopropylmethyl carbocation. Yeah. How it is going to stable? Right. This is a cyclopropane, and here this is a cyclopropyl. It is carrying positive charge CH2 plus. Okay. Yeah. Now here this carbon is undergoes sp2 hybridization. Yeah. Now sp2 means one s orbital and two p atomic orbitals are intermixed. You will get sp2 hybrid orbitals. Okay. Still in the p orbitals, one is not participating in intermixing. There is unhybridized p orbital. That is called pure p atomic orbital. So that means this carbon have one pure p atomic orbital. We, for our convenience, I just represent for our convenience to understand. Okay, you can represent like this. This is CH2 plus. Okay, right? So this carbon undergoes sp2 hybridization. sp2 hybridizers are there. Okay, yeah. Now this carbon having one pure p atomic orbital, right? This is a pure vacant, that is empty, right? Pure vacant p atomic orbital. AO means atomic orbital, right? Now if this pure p atomic orbital is getting electrons, then that is going to be stabilized, the carbon carrying positive charge. For that, the adjacent carbons, that is sp3 carbon, this carbon is sp3 because here 1, 2, 3, one hydrogen is there. Here also here two hydrogens are there. So all are sigma bonds. 1, 2, 3, 4, all are sigma bonds. So this carbon also undergoes sp3 hybridization. Yeah. Okay. So sp3 hybridization means here this sp3 hybrid orbitals are overlapped to form sigma bond here, right? That means here this here the orbitals present in here. The orbitals present is sp3 hybrid orbitals. Okay. Okay, this is sp3, this is sp3. This carbon provides sp3, this carbon provides sp3. These two sp3 hybrid orbitals are overlapped along the intermolecular axis. Then you will get a sigma bond, right? Okay, there is a sigma bond. This is sp3 sigma bond, right? Sigma sp3 bond, right? Yeah. Now, so they have electrons, right? They have electrons. Okay. Now, this sp3 hybrid orbitals. This is sp3 hybrid orbitals. These are electrons rich. Their electrons are there. Electron rich. But this is vacant orbital means. It want electrons wanted in this one, electrons wanted, here electrons rich are there, there is this two electrons are there, right? Now this bond, this is sigma bond, this is a sigma sp3 bond, right? This okay, this bond, this sigma bond is bend, okay, it is just move like this and reaches closer to the pure vacant orbital and overlap with that, then it is getting electrons. Then the positive charge is partially fulfilled by these electrons. Then it is going to stabilize, right? That means here the sigma bond between the two carbons, okay, bended, okay, the sigma bond bent and reaches closer to vacant p atomic orbital and overlapping. Okay, so overlap with the pure vacant p atomic orbital. Okay, it is overlap with the vacant pure p atomic orbital, right? Once it is because of that, what happened? Then the electrons are getting this vacant pure p atomic orbitals. That's why now it is the positive charge is partially filled with this, fulfilled with these electrons. Okay, the positive charge on carbon is fulfilled, partially fulfilled with these electrons, okay. Yeah, now this is stabilized. And also not only this one, ma, this is also there, right? This is also there, right? This is also what the sigma bond, this carbon that is sp3 these orbitals also electrons, they may be here. So this is what happened, these electrons, when this is there, they move like this, they flip here and they overlap with this one also. So this is also participate like this, and this is also they flip here and it is also participate, these 5 electrons, these sigma bond electrons, sp3 sigma bond electrons, they may be overlap with this, okay, like this. So this and this all are possible here. So that's why it is extraordinarily highly stable carbocation. Okay, it is highly stable carbocation. Extraordinary highly stable carbocation. Got it? Yeah. Okay. So this is about the stability of cyclopropylmethyl carbocation. Okay. Got it, ma? Right? So this is the clear concept I gave. Just copy it. Okay. So generally students are confusing. Sir, it is CPM carbocation. How it is stable, sir? You didn't get proper explanations in the books. Okay. So this is the complete explanation I gave. Got it? So from this side or this side also it is possible. These electrons, okay, and this sigma sp3 sp electrons are also they flip and overlap with us. Then it is getting stable from all these things. So that's why it is extraordinarily highly stable carbocation. Is it clear? Okay. So here this is a pure vacant p-atomic orbital, and this is a sp3 hybrid orbital. This atomic orbital, this is vacant, this hybrid orbitals, this is filled with electron rich, these electrons are there. So that it bends, this just from here it is bends like this, from here it is bends like this and reaches closer to the sp3 vacant p orbital and overlap with that, and it is giving electron to that. Then it is the positive charge is partially fulfilled, then it is going to stabilize, readily stable. So that's why it is actually stable carbocation. Right? Is it clear? Yeah. Next one. Is it clear? Can I erase it now? Fine. Next one. So this is bends, and it is also it moved from here. It is not possible on showing on the board. So in the 3-dimensional arrangement, it moved here from here back side. It moved and it giving electron to that. Got it? Yeah. Next one. Here this is also, in this case here, so 1, 2, 3, 4, 5, 6, 7 carbons. This carbon is carrying, it is getting positive charge, and here pi bond is there, pi bond is there, pi bond is there. Okay, yeah. Next one, you represent like this. 1, 2, 3, 4, 5, 6, 7. Here positive charge is there, and here pi bond, double bond, here pi bond is there. Yeah. Next one. And it is 1, 2, 3, 4, 5, 6. Okay, and here positive charge is there, and here pi bond, yeah. Next one. Here CH2 plus, okay, CH2 plus, and here what you will get, it is here, it is a double bond, and here double bond is there, right? Okay, fine. Now in this case, so they will give sometimes it is CH2, or you just represent one previous year examination just giving now. So this is here, this is plus, there is nothing but what here CH2 plus 1. Okay, got it? Yeah. Now they will give like this. Now which among this is highly stable, and what is the order of stability of this one? This It is all-time favorite question mark. Got it? Yes. All-time favorite question. Okay, fine. Now, here, this carbon carrying positive charge. These pi electrons are shifted over here. It is getting stable. These are shifted over here. These are shifted over here. Right? So, this type of conjugation, here conjugation is there, right? Double bond, single bond, positive charge. Okay, this conjugation, we can call it as a linear conjugation. It is a linear conjugation. Linear conjugation, right? Okay. Then what about here? Here positive charge is there here, right? Yeah. So these pi electrons are shifted, delocalized and make a under bond and it is getting stable. Or these pi electrons are delocalized and getting stable. And they make this getting positive charge, these pi electrons over here getting stable, right? Yeah. So this type of conjugation is called, it is cross conjugation. Cross conjugation. That is here, cross conjugation means it is getting stable from this side also, from this side also. Got it? Yeah. Okay. Next one. In this case, this carbocation, it is unstable. Then this pi electrons over here is getting stable. This carbon gets positive. This is migrated over here. Then it's getting stable. Right? Okay. Yeah. Next one. Here, it is also what type of this? This linear conjugation. Linear conjugation. In this case, CH2 plus, right? Here, this pi electron is over here. Yeah. Then gets positive charge. This is migrated over here. It is getting positive charge. This is migrated over here. It is getting positive like that. It is stabilized by this pi electrons are migrated along the length of the carbon chain. So migration of pi bond electrons along the length of the carbon chain in a cyclical manner. This is called cyclic conjugation, cyclical conjugation. Yeah. Here also there is a double pi bond, sigma bond, positive charge. Okay. So pi bond, sigma bond, positive charge. Okay. So that's why this is called what? Conjugation. Okay. So this conjugation, it is maybe linear conjugation or cross conjugation or cyclical conjugation. Which among this is highly stable means in case of cyclical conjugation, there is getting more stable, right? So that's why among this, the order of stability is highly stable is D. Okay, okay, yeah. Next one is here linear and cross linear. Okay, of this linear and cross, which one? Linear conjugation gives more stable, that is A. Then of this here, it is also linear, but which is here. Here next one, how many pi bonds are there? 1, 2, 3. Here 1, 2. So there is, if the two are linear conjugation, the next factor is number of pi bonds. Number of pi bonds is more. What about more delocalizations take place? Charge dispersal is more. Dispersal of charge is more. Then stability is also more. Okay. So here number of pi bonds is directly proportional to stability. Okay. Or you can say total number of bonds. So here number of pi bonds are in this case is less. Okay. So that's why it is less stable. And here, so here 3 pi bonds are there, here 2 pi bonds are there. So here 3 pi bonds are there and here 2 pi bonds are there. So that's why it is highly stable than this. Okay. So that's why next B, next C. Got it? So this is the order of stability of this different carbocations. We can explain under the linear conjugation, cross conjugation and cyclical conjugation. Is it clear? Got it? These are all new concepts right for you. Fine? Yeah. Next one. One more thing here. It is also last previous year question. Okay. This is also last previous year question. They frame the question like this. Yeah, I just I'll give to you a practice question. You just write that one. A practice question. A practice question. So they frame the question like this. Yeah. Double bond, double bond, double bond. Okay. And then here positive charge, double bond, double bond, double bond. And then here positive charge and here double bond, right? Okay. So this is also previous year examination question, my dear students. So which is more stable and what the order of stability of this one? Okay. Just to try it, I explained Okay, from this, if by watching this, you can easily understand. By applying that concept, by using that concept, you can easily answer it. Okay, in the next video, I will just give solution for this one also, and then in the next video, some more compounds are there. These are all specially stabilized carbocations, and some more examples are there. So that is we are going to do in the next part 3. Okay, in that different models of carbocations are there that appear different company examinations. There is from some or KVPY examination questions are there, and KSET and TSET and MSET and AIMS questions are also there. Okay, some advanced questions are also there. So this is all from carbocations stability. Generally, we can expect one question for NEET or JEE mains or advanced. So that's why it is very important, my dear students. So that's why some more concepts you'll get it in the next part. I'm giving to you some different models of exam questions, examination questions. Okay, so there you can get it. You can enjoy the carbocation stability, clear concept, everything about carbocations. You will get it. Yeah, fine. Okay, so thanks for watching my video. Like it, subscribe it, and share to your friends. Fine.